next and the last speaker is Giorgio, and he's telling us about the Lagrangian approach. So we start.
Okay, thank you very much. I will speak, what I will speak about is summarized in these papers. You see in the title, and they were done in collaboration with David Montenegro and Leonardo Tinti. I will speak in the results are shared, and the results are shared. Some of the interpretation is mine. So I just want to say that it's personal capacity because they don't necessarily agree. I hope they do, but yeah. First of all, thank you very much for inviting me. Conferences, this is a very difficult subject. It's still not really well developed. And what compensates is these conferences are a real joy. The level of discussion that has been going on, the deep physics discussions are difficult to see in conferences and even other sub-subjects of like heavy ion physics. And I want to thank the organizers now that this conference comes to an end. The only thing which unfortunately is missing is the Pedavena, which is the brewery in Trento where every session usually ends up in the conferences physically there. One should be able to export it into Zoom, but unfortunately I can understand that this is a bit difficult. So what am I going to talk about? I would like to convince you that some characteristics of the subject, which have been reflected in the discussion of the last 2 weeks, are optimized to be analyzed by treating hydrodynamics as a Lagrangian field theory and starting from there. Otherwise known as bottom-up effective field theory techniques. They have a disadvantage in the sense that we do not, most people at this conference try to take the microscopic approach and calculate stuff from it. Here, this is not done. Things like viscosity and polarizability are black boxes. We have limited insight into microscopic physics beyond the fact that things are assumed to thermalize fast, God knows how. They have these symmetries, and of course, we like Lorentz invariants, and we like causes to be before effects. However, and I have to say that the discussion of the last 2 weeks really convinced me of this, some insights, some very profound insights are very simple and intuitive. And what was very interesting is that these insights are being confirmed by speakers. It has given me a lot of pleasure to see that these insights are actually being confirmed and re-derived in different ways by people working on different approaches, which actually seems to say that they're sound, because if one of the criteria for soundness is that different approaches give the same result. So everybody saw this picture in one way or another. It made the cover of Nature. Vorticity seems to polarize lambdas. It was a spectacular result. And one question I get from people from other areas of heavy ion physics is, okay, the picture is pretty, but what have we learned about quark-gluon plasma? Like, what do we know? How much does it add to our knowledge? To me, my answer is it adds questions that we as theorists must answer. Hydrodynamics is often seen as an effective theory of transport, an effective theory of the Boltzmann equation, an effective theory of ADS-CFT, and blah, blah, blah. However, it's more than this. And it's more than this, and this experimental result forces this into us, because what we're seeing is that collective excitations, such as vortices, back cascade into microscopic entropy configurations, such as polarization. This means that the Boltzmann equation, which is reliant on molecular chaos, and transport approaches, which are reliant around things like quantum occupancy number of what is called the H-bar expansion, and ADS-CFT, which relies on NC, I will talk about it later, they might be correct, but they rely on expansions of which this this experimental observation signals it could diverge. Because backscattering of macroscopic perturbations into microscopic entropy configurations is exactly the thing which is a small parameter in these expansions. It could be that it's small enough in experiment too. However, one has to be careful. So one must try to go beyond this approximation. How do you do it? Well, what is Lagrangian hydrodynamics? Lagrangian hydrodynamics, it's named both after Lagrange who developed it, but it's also based around the Lagrangian. The fundamental degrees of freedom are the coordinates of a particle cell, at least without polarization. The fundamental degrees of freedom are the coordinates around particle cell, and the assumption that goes into the effective Lagrangian is instant thermalization. Intuitively, what happens is if you have local equilibrium, by assumption, you assume that you have local equilibrium. What does this mean? This means that energy is locally minimized. Energy is minimized from the beginning to the end. This gives us a very simple relation, a Legendre transform between what a Lagrangian in classical mechanics should be and the free energy. And indeed, usually in Lagrangian hydrodynamics, the Lagrangian is nothing else but the Legendre transform of the microscopic free energy. There are certain symmetries. Incidentally, excitations of these are usually Goldstone bosons, and causality can be checked by linearizing and finding the dispersion relation. For instance, without polarization and without chemical potentials, a fluid has these symmetries here. It has translation invariance, it has homogeneity and isotropy, and it has invariance under volume preserving the diffeomorphisms. This, incidentally, the Noether current of this can be shown to be related to Kelvin's theorem, to the conservation of circulation. If you plug these into the microscopic degrees of freedom, which, as I said, are the Lagrangian coordinates of the co-moving cell, the cell that expands, it's relatively straightforward to check that the Lagrangian can only depend on B, which is nothing else but the volume element, the equivalent of minus G in general relativity, the local metric. Of course, it's the metric of the co-moving space. It's not space-time because this is not general relativity. And indeed, if you write the Lagrangian like this, it's very easy to see that you get the energy momentum tensor of ideal fluid dynamics by differentiating the metric. So why is that cool? This is cool because, as was reiterated, Dirk said this early this week. I'm trying to also make a summary talk here as well as my own results. And I remember Dirk, during the discussion, reiterating many times this very important point. Hydrodynamics is not based on 2 scales, it's based on 3 scales. It's based on a hierarchy of 3 scales, which is the microscopic scale, which is simply the distance between degrees of freedom. If you want, it's the entropy to the minus 1/3. The mean free path, and the macroscopic scale. What we call the Knudsen number is the last equivalence. The mean free path has to be smaller than the microscopic scale. The thing that I said that makes a lot of approaches that we use suspect is the fact that the vorticity is here. It's a macroscopic Lagrangian, and polarization is here. It's the microscopic degree of freedom. So we really have to thread carefully, because if these 2 guys directly talk to each other, this whole system is very suspect. And the Boltzmann equation is based on the first inequality. That's what guarantees molecular chaos. The large NC expansion is also based on the first inequality. This guy here is reverse of NC. Depends on a higher reverse power of NC than this guy. And what it means is exactly, and if it turns out that these 2 scales talk to each other, it also means that sound waves of very high frequency and of amplitude given by thermal fluctuations also talk to each other and also modify the gradient. And this is basically the question: what do thermal fluctuations do to a fluid when viscosity is very small? It's small enough for thermal fluctuations to live for a long time. Lagrangian hydrodynamics could be better poised to answer this question because of the fact that the Lagrangian comes with a microscopic scale in the Lagrangian. This B is dimensionless, and therefore there must be a scale of the energy density in front of the Lagrangian, which, as I said, is a Legendre transform as a free energy. This scale is actually sort of like a Planck's constant. So a complete series in a Planck's constant in the regime of vanishing viscosity, we're not necessarily asking, we're saying that viscosity is small, but fluctuations could be big enough that a series based around the Planck's constant expansion that many transport groups have used throughout might diverge. This limit is, at least in principle, accessible to Lagrangian theory, because what happens is what happens when you quantize or thermalize any other system of which you know the Lagrangian. You set up a functional integral and then you calculate correlations. The problem is that it's not a very perturbative theory, as you will see. You can also put in dissipation using essentially Schwinger-Keldysh techniques. That's all there is. You have two propagators, one into equilibrium, one away from equilibrium. So what can you do? You can try to do perturbation theory with sound waves. In a hydrostatic limit, at least, the Lagrangian and the lab coordinates match, and therefore the expansion is like this. You have the Lagrangian coordinate equals the lab coordinate plus a sound perturbation and a vortex perturbation. Sound is in a certain direction, vortex is perpendicular to a direction. And when you expand the Lagrangian, you find a sound wave, which is a relativistic particle, and we know that because particles propagate at the speed of sound. And you also find a type derivative only for the vortex. And we know this because vortices don't propagate. I mean, if you set up a vortex in liquid helium, it will just keep spinning. However, this Lagrangian here is a disaster for people who want to analytically continue doing calculations, because it basically means that it destroys all perturbation theory. Because if you want thermal fluctuations and quantum fluctuations, if you want, will create vortices, and the vortices will just stay there and pile up and destroy the vacuum. On the lattice, we find this is the paper, traces of a phase transition, but this is still, there is no evidence for this. Incidentally, to resolve this instability, you need to give a gap, an energy gap to the vortex, and this is could be the role of polarization. You can extend this whole formalism to chemical potentials in a very beautiful way. In the ideal hydrodynamic limit, the entropy current and the current of a conserved charge are parallel to each other. And this can be, in the Lagrangian formalism, this is equivalent to a symmetry, which is called chemical shift. There is a very beautiful paper I should have cited by Alberto Nicole's son and Dubovsky, if I remember correctly. And they derive this ideal hydrodynamic limit in terms of the chemical shift symmetry in the Lagrangian. What basically happens is that an internal symmetry is a phase. The phase has to depend on space coordinates, and it turns out that any diffeomorphism of the space coordinates has to leave the phase invariant. And the only way this can happen is if the conserved current is exactly proportional to the entropy current. They have the same direction. And this is what happens. And the phase then becomes related to the conserved current this way. And the chemical potential, you can derive the chemical potential by standard statistical mechanics techniques. Very nice. Now we're kind of ready to think about what happens if we also add polarization. So this is, to me, a conceptual question. Before you do calculations, you really have to think, which is really nice. because it doesn't always happen, and thinking is nice. So what do we mean when we mean the ideal hydrodynamic limit? Well, we could mean, as I said, that the entropy is conserved. The entropy forms a conserved current. We could also mean local isotropy, but with polarization, this is certainly not the case because there is a spin and it points in a certain direction. We can also mean Kelvin's theorem, vortices last forever, circulation is conserved. But this can also doesn't happen because polarization, this is actually another current for deformations, but this is broken because polarization absorbs and emits angular momentum. And this alters the circulation. We can also mean continuum limit, but polarization, there is the de Broglie wavelength beyond which you have a quantum particle, and polarization is related to this, and circulation is associated with the surface, is associated with a loop. Now think of like Wilson loops of QCD. So continuum limits you can do only in certain limits. The only one of these criteria which appears to work is the conservation of entropy, which is very simple to capture in a Lagrangian, theory. So my definition of ideal hydrodynamics is that in the semi-classical limit, if you take fluctuations away, entropy is conserved and polarization density is non-zero. So what happens then? Well, my equivalent of the H-bar expansion is all here. If we go back to these famous 3 length scales, which have to be in this hierarchy, it is very clear that polarization is controlled by the same scale that controls thermal fluctuations. Why? Because fluctuation is a collective excitation that carries no entropy, while polarization obviously controls microstates. If everything has to point in a certain direction, microstates change. So these 2 scales have to talk to each other for polarization to be non-zero. With this intermediate scale, if you believe the ideal hydrodynamic simulations for V2, etc., has to be very low. Polarization is generally a 2-particle correlation. It's a 2-particle microscopic correlation that says that if one particle points one way, the other particle will have a conditional probability of pointing another way. And of course, at least for fermions in a planar limit, polarization is typically suppressed by a power of NC. So understanding polarization is similar to understanding the role of fluctuations. However, polarization is also related to angular momentum, which is a conserved quantity, and that can help. Combining all these insights comes out with these characteristics, which you can straightforwardly put in a Lagrangian. The way I see the implementation of polarization is similar to the implementation of chemical potential. Except, of course, a chemical potential is a scalar charge, and spin has the symmetries of either a SU2 or a SO3. The difference, of course, there is a difference if you do quantum mechanics, but we think of many particle limits, so we think that phases all alter out. I mean, there was a talk by Xinli Sheng about continuous spin, and this is a very similar thing. So basically, polarization is a chemical potential which transforms under an algebra of the angular momentum transformations. And we can define an antisymmetric matrix U alpha beta in the same way as with a chemical shift symmetry. Note that this is an analogy. This is an intuitive analogy, and it's not really a chemical potential because spin is not a conserved quantity. In fact, spin is bound by local equilibrium. However, the chemical potential will have to be, however, the free energy will now not just depend on the microscopic volume element B, which was capital B, small b here, but it will also depend on this Y, which is the, you can think about it as the chemical potential of polarization components. The global symmetry, I mean, the symmetry might be broken, but the global symmetry is still, the basic symmetry of the Lagrangian is still invariant under rotations, and therefore the lowest order transformation is equivalent to mapping the entropy into 1 minus or plus y squared into the polarization squared. The coordinate could be negative or positive, and this is very similar to ferromagnetic and antiferromagnetic or paramagnetic materials. Of course, they're not magnetic, they're vortetic because there is no magnetic fields here. And therefore, let's call them ferrovortetic and antiferrovortetic to avoid confusion. But the effect is basically the same. A ferrovortetic material, the free energy will generally decrease if the system is polarized, and antiferrovortetic material, the free energy will generally increase. Will generally increase. And the first law of thermodynamics is going to be something like this. You're going to have an entropy multiplier with respect to the free energy, and you're going to have a polarization multiplier with respect to the free energy. The ambiguity of the energy momentum tensor, which has been discussed at length here, in the Lagrangian approach is completely irrelevant. Do you have different energy momentum tensors? They're all conserved. They're all different by a boundary term. However, there is no consequence because dynamics, if polarization is present, hydrodynamics is not an effective theory of conservation laws. There are not enough conservation laws to close the equations. It's an effective theory of entropy maximization. It's an effective theory of free energy minimization. And therefore, the energy momentum tensor is something that you might want to calculate, but the conservation of the energy momentum tensor is not going to give you dynamics. The minimization of the free energy between paths will give you the local dynamics. So how do we construct the free energy? Well, it's going to look something like this. You're going to have a pressure term, you're going to have an energy density term, and you're going to have an angular momentum term, which controls the variation of entropy with respect to the vorticity. And it's going to have this form here. Well, this guy here is the vortical polarizability, and you're going to have the conserved vorticity, which is the conserved angular momentum here. However, the Lagrangian approach immediately gives you a very important consequence. For this limit to make any kind of local sense, the polarization and the vorticity have to be parallel to each other. Radoslav talked about this in terms of a killing vector argument, that in a global equilibrium, the killing vector forces vorticity and polarization to be the same. However, you have to be careful because in microscopic theory, the two don't have to be the same. If it's a fluid based on polymer molecules with a weird shape, and I mean, Edward Chiriac and collaborators have been talking about the strongly coupled quark-gluon plasma in this form for ages, then this guy here is going to be a matrix, and in general, polarization and vorticity will not be the same. However, if you include polarization, you will have two vector quantities here, which are polarization and vorticity. If the two do not point the same way, you will have a Goldstone mode, which is the mode which is parallel to each other. And if you have the Goldstone mode, after you have a ideal limit, you are in trouble because this ideal limit is multiply defined. You will not find a local minimum for entropy, and essentially the Goldstone mode will act as a second sound, will act as what Landau called the second sound. The vibrations carrying no energy vibrations with no energy gap will carry entropy from one volume cell to the other, and this will destroy macroscopic local equilibrium, even if microscopically the system is in local equilibrium. So for ideal fluid with polarization to have something like a local equilibrium minimum, polarization and vorticity have to be proportional to each other. Once you have this, you can easily derive the Euler, not easily, I mean, this was actually a pretty complicated calculation. It's complicated by the fact that the Lagrangian depends on acceleration, but you can find a set of Euler-Lagrange equations. They actually have the same form as conservation law equations, And the conserved quantities here are the angular momentum components of the co-moving volume. So that kind of makes sense. But the components themselves are pretty complicated currents, functions of both vorticity and this polarization variable. So now we can linearize. So now we can linearize exactly like we linearized before. We find that sound waves and vortices mix, which again is intuitively obvious because a sound wave raises temperature, a sound wave raises temperature, temperature generally changes the susceptibility, and this changes the vorticity. Therefore, sound waves and vortices obviously mix. However, in a sense, this solves the linear stability problem at the time, but it actually doesn't solve, it actually introduces a new problem, which is causality. To leading order, the dispersion relations are non-causal. To leading order, the dispersion relations are non-causal. What does this mean? Well, I think that we found the same thing as the group of Dirk and Nora found with respect to the non-local collision term, but from a completely different approach. We assumed that the free energy, depends on polarization. Thermalization is instantaneous, and therefore changes in vorticity immediately lead to changes in polarization. This leads to instantaneous mixing between sound waves and vortices, and this is what violates causality. If we introduce a relaxation time between vorticity and polarization, we find that provided in an antiferrovortetic fluid, provided that the relaxation time is bigger than a certain combination of polarization, speed of sound, and pressure, provided that this is true, causality is restored for ultraviolet modes, provided that causality is restored. This is a very neat result because in a sense, this is a bottom-up limit on viscosity. I mean, if we assume that the microscopic particles have spin, we assume that there is a certain amount of polarization in them. And if there is a certain amount of polarization in them, the microscopic viscosity has to be bigger than zero. This is a much more realistic, set of assumptions than there were limits on viscosity found before. I mean, Danielowicz and Gulaschi found them in the 80s from the Boltzmann equation. Then, of course, there is the famous Kss bound. This is a bound on viscosity simply based on the fact that microscopic particles have spin. So that even if the system is strongly coupled enough that it thermalizes instantly, the presence of polarization has to introduce a bottom-up limit on viscosity. And I'm very happy to see that both gradient expansion type approaches and transport approaches, which we've all heard here, seem to yield the same conclusion. As Feynman said, theory should be able to have at least 3 explanations of the physical phenomenon. The physical phenomenon here is that particles have a de Broglie wavelength, and vorticity should cause spin flips, and these spin flips should be independent of any kind of mean free path, because even if thermalization happens instantly, you have position uncertainty thanks to the de Broglie wavelength, and this introduces a relaxation time. Such a relaxation time also introduces a complex. Yes.
Andre, let me mute. Okay.
Yeah. So this relaxation time introduces a soft energy gap. This relaxation time also introduces a short energy gap, which might resolve the stability against fluctuations of ideal hydrodynamics that I talked about before. This was a This was of a speculation. To a certain extent, it still is. However, in this paper here, my student David Montenegro has conducted a real tour de force calculation where the polarizability and the relaxation time are really connected to by a Kramers-Koenig relation, just like usual fluctuation dissipation theorems. We also found that polarization acts a little bit like a Higgs mechanism. Certain vorticity components acquire a gap. It's not a mass gap, it's a dissipative gap, but the mathematics works in exactly the same way. And you have some spin components that get eaten and acquire mass and others don't, et cetera, et cetera. Tails of correlation functions of these guys have exactly the same behavior as the tails of fluctuating hydrodynamics, which was derived by Coughton, which reinforces the idea that fluctuations and polarization are connected. And we find all Kubo formulas for every kind of correlator that I talked about. They're complicated. It's a complicated calculation. We still have a non-causal infrared mode. We still have a non-causal mode for ferrovortetic fluids, but we expect this. We expect this because this is nothing else but the equivalent of the Banks-Kasher mode for unstable vacua. As you know, the one classical result of field theories with broken symmetries is that you have an infrared superluminal propagation. You will have an infrared superluminally propagating mode, which is not a superluminally propagating mode. It's an indication of the instability of the vacuum. And you can also use it to define a gap equation where the vacuum is truly stable. And therefore, we expect that the ferrovortetic fluid will become causal once this gap equation has been done. The EFT that I constructed is unreliable in this case because one must construct a new EFT from the gap equation. In the future, we will do this. How much time do I have? Hello?
You have, 8 minutes.
8 minutes. Oh, thank you very much. Wow, I talk fast. Everything I talked about is theoretical. We've used, and I forgot to say that this gap, this causality violation is actually also related to a classical theorem in Lagrangian field theory, which is called Ostrogrotsky.
Sorry, 8 minutes including discussion, maybe.
Including discussion. I see. Okay. So I will wrap up in 2 minutes. Called Ostrogrotsky's theorem. Okay. So everything I said up until now is theoretical. Phenomenology is all future projects. So the question is, can we find traces of polarization before freeze out in the hot phase? Well, what can we say? I mean, there is dilepton and photon polarization, provided experimentalists can measure it, could give hints about pre-existing polarization, It's dubious whether experimentalists can do it, but people have proposed it before. Vector mesons are a little bit more hopeful from the experimental point of view because we've already seen spin alignment. And the point about vector mesons is that their density matrix isn't a vector in SU2 space, it's a vector in it's not a matrix in SU2 space, it's in a vector in SU3 space. And there is a lot more information to be collected. Because the angular distribution with respect to the two azimuthal angles is sensitive to the whole density matrix. The point is that longitudinal and transverse polarization are formed on very different time scales. The transverse polarization is formed initially at the initial collision. The longitudinal polarization is formed with V2. And if it's really true that there is a relaxation time between vorticity and longitudinal vorticity is formed when V2 is formed, transverse vorticities formed initially. And if it's really true that there is an equilibration time between vorticity and polarization, then transverse vorticity should be a lot more equilibrated than longitudinal vorticity, and we might see it once the full angular distribution of vector mesons is measured. Also, the Cooper-Frye formula shouldn't really work because both you need a freeze-out that incorporates both spin and angular momentum, not just the total angular momentum. There is going to be some kind of coalescence Wigner function, and one can test this, with vector mesons because of the fact that vector mesons have a lot more information. They're SU3 instead of fermions, which are SU2. It could be, you could test for coherence, for example, for coherence of the density matrix. This is ongoing work with my student Kaiman. I mean, further theoretical developments are trying to make a match with Zuber of hydrodynamics. I gave a whole colloquium about this 2 days ago, and it's on YouTube for people who are interested. And I think this is a good time to stop. I just want to say that there are profound insights about gauge theory in this approach, about non-abelian gauge symmetries in particular, which are important for gluon polarization. And if you want to ask me about this, I will answer. Thank you very much.
Okay, thank you very much. So now, questions. I guess that lots of discussions. Okay, Francesco first.
Hi, Giorgio.
Hi.
Can you go to the slide where you show the separation of scales?
Sure. Oh, wow.
Yeah, this one. Yeah. Okay. So I don't understand. I don't understand really why you want to have the mean distance between particles, because this is n to the minus 1/3, means this is the average distance between particles or between constituents. Why you want this to be much smaller than the mean free path for a fluid? Because, for instance, for plain water, this is known to be the same. So the mean free path is approximately the same. I'm not talking about gas. I'm talking about liquid water.
Sure. Very good question.
The mean free path is approximately the same as the distance between molecules.
Very good question.
So the question is why? I mean, I would expect you to write something related to the thermal wavelengths of particles rather than
no.
The
thermal wavelength is related to the microscopic scale in a relativistic system.
I agree. I agree. It is a microscopic scale. However, so my question is why you require that the mean distance between particles to be much less than mean free path.
Yeah. So your water example is excellent. And maybe we shouldn't talk about mean free path. We should more talk about scattering length. Because the point is, in water, you don't have scatter. Water is an example of a system where hydrodynamics works really well. Hydrodynamics works extremely well, but the Boltzmann equation...
By naming, I would say, yes.
Yeah, exactly. By definition. But the Boltzmann equation works in a very lousy way. And the reason is that water molecules, you have hydrogen bonds. Water molecules are all highly correlated, and there is no scattering of water molecules in water. So the mean free path, we shouldn't...
I cannot understand this.
Inside water, water molecules don't scatter because they're not free. Scattering means you have a free state in the beginning and a free state at the end. In water, this never happens. Water is also...
No, I don't understand it. I mean, well, okay.
Yeah.
It depends on maybe... Maybe this depends on how you define scattering. However, I mean, in water, what happens is the thermal wavelength is extremely smaller than the mean free path. So you may think of classical objects which collide. It's a fact that kinetic theory works for water.
Sorry, can I interrupt you guys for 1 second? I think one thing is missing here in this inequality, which is the range of interaction. If you have long range interactions like in water, it will,
instead of mean free path, this inequality should talk about the range of interaction. You're right.
No, I'm not sure this is the same, Giorgio, because the mean free path factors in the thermal wavelength, but while the range of interaction is simply some microscopic property of your interaction.
I mean, within a Boltzmann equation, what this inequality is needed, because what happens is that for scattering to be a good approximation, the particle has to pass through lots of particles beyond scattering. And this is what the first inequality means, that that there is an uncertainty with what particle will every particle scatter. And this is what you get for molecular chaos, or if you want, in the H-bar, in what is called the H-bar expansion, it's sort of the first term. In water, particles keep being correlated with each other. They don't move freely. I agree with this. They don't move freely, but there is also something else. Water is incompressible, basically. Water is incompressible. Within a relativistic limit, incompressibility is impossible because of causality. Speed of sound has to be smaller than the speed of light. So if you try to make water compressible, compressibility essentially means that particles, microscopic particles, have to move around. And in the ultra-relativistic limit, this becomes this chain of inequalities here. In water, because of the fact that it's a non-relativistic system, which is also incompressible, and the water molecules are close to each other, the definition of mean free path becomes something which is non-trivial. I agree with this. But I think that water is a very good example for a system where hydrodynamics works and transport doesn't.
Can I say something? So in order to have the first inequality, so you need to have some small parameter, and only in that case you can safely define what is a mean free path. And it is, I think that means that if you have the weak coupling quantum field theory, you can justify the use of the Boltzmann equation so that you have the microscopic length and the mean free path separately. But if you have the strong coupling theory, like the n equal 4 super Young Mills, you cannot separate them. So in order to have this 2 times 2 scale in microscopic and mean free path, you need to have some small. So
you do, because the intermediate scale is eta over st, right? In ADS-CFT, the intermediate scale is eta over st, and the microscopic scale is nc to the minus 1/3. And for classical gauge gravity duality to work, you don't just need strong coupling. For classical ADS-CFT gravity to work, you need NC to be much bigger than coupling. So the coupling is infinite, but NC is infinite squared. And this hierarchy still works. And this is the assumption, to me, I mean, if you ask me why I don't believe in ADS-CFT for heavy ion collisions, it's actually this. We know what NC is, and it's 3. And it seems, I mean, between the vorticity result and the result of the PP collision, fluid-like behavior in PP collisions, this to me shows that, and it could be that the coupling constant is very strong and the system thermalizes quickly, but NC is not bigger than that. NC is not bigger than the coupling constant. And in fact, the stronger the coupling constant is, the bigger than 3 it is, right? Yeah. So ADS-CFT is also, this hierarchy also works in a different form. And by the way, to answer to Francesco, since this was mentioned, the intermediate scale, a good definition, a more general definition of the intermediate scale, the sound wave dissipation length, eta over st. And in water, this works very well because in water, sound waves go much faster. In water, sound waves go much further than the thermal wavelength, right? So yeah, in water, this hierarchy works.
Okay, so yeah, I think that this is a very interesting question. What should be the hierarchy, the scale hierarchy for liquid in general? So, but because the time is limited, so let's go to the next question by Chun.
Yeah, Giorgio, very nice talk. But my question is about the relationship between the polarization and the ground state of the hydro system. So
And
what's
what,
your
sorry?
conclusion? You mean if you consider the polarization or spin polarization, then you say that the ground state of the fluid is not some statement about the ground state. So what's the relationship between this polarization and the ground state of the fluid? So what?
You mean global versus local equilibrium, right?
Yeah, exactly. So what's the conclusion?
You mean global versus local equilibrium? Well, look, yeah. Okay.
Does it has something to do with the stability?
It does. It's a good question that I still do not know how to think about. I think the best way that I can think of thinking about is with Zubarov together with Crookes' fluctuation theorem, and unfortunately this would be a completely different talk. The point is that global and local equilibrium become very different things. So global equilibrium, the one that, Andrea Palermo talked about and Georgi Prokhorov talked about, global equilibrium is when you maximize entropy with respect to a bunch of Lagrange multipliers, which incorporate the non-inertial frame, transformation. Local equilibrium is when the KMS condition is locally justified. The local equilibrium is when the KMS condition is locally justified. Now, entropy is a frame-dependent quantity. Entropy is a frame.
Giorgio, I completely disagree with what you said. I mean,
okay.
The global equilibrium is when you maximize entropy with conserved integrated charges, including, say, those of the Poincaré group, namely angular momentum, boost, and momenta. And it has nothing to do with non-inertial frames.
Yeah, but when you accelerate, it's a non-inertial frame. When you rotate, it's
the frame doesn't matter. I mean, this is completely covariant expression.
Well,
so you can make it. You can maximize entropy with these constraints covariantly. So it has nothing to do with frames.
But entropy is frame dependent. Entropy is
not frame dependent. Total entropy is minus trace rho log rho is not frame dependent.
What about the Unruh effect?
Unruh effect has nothing to do with entropy.
Well, I mean, finite temperature also means that you have an entropy density, right? The question is, I could be wrong. This is a very subtle issue, but the question is, if your global equilibrium state isn't also in a KMS state, with respect to the co-moving frame, it might be unstable. And what exactly does that mean? what does it mean to have a local equilibrium state which is unstable? You have a, what does it mean to have, you have a global equilibrium state, which is non-local because it's rotating around, and an instability might actually destroy it. So in what sense is it global equilibrium? You see what I'm saying?
Yeah, okay, so this is a
total
complicated
entropy does depend on total entropy. If you are in a non-inertial frame, you do see a different entropy when you are in an inertial frame and a different pseudo gauge. Masaru Hongo, I think, talked about this a little bit.
Okay, I think that the discussion is very interesting, but so this is, I know this kind of argument, but I'm also very much confused always. And so we should definitely continue discussions. But anyway, we should close this session. And so let's thank Giorgio again. Very nice talk. Thank you very much.